our last topic for the subject. And as I mentioned last week, we have basically 2 weeks to talk about the multi-degree of freedom systems. So this week is a continuation for what we talked about last week. Last week, basically, there was a decent math process beside applying some dynamic engineering decisions, where we ended up with the equations of motion, and it was represented in a coupled format. What does that mean? It is represented in a matrix format. Simply, this is today what we're going to be starting with. Before we start again looking to the math, I will just take you through the story behind when the mode shape is kind of can be confirmed in a system, or when the mode shape's going to happen. When we have a single degree of freedom system, simply we have one mode shape, because a single degree of freedom system, which is something like, let me zoom here, and a single degree of freedom system is just one mass standing on one support, and as we all can agree about, it will have one shape to vibrate with. It will vibrate this way, that's shape 1, or vibrate this one, which is same as shape 1. So that's one mode shape. It's got one shape, full stop. When we're going to have 2 degree or more, the mode shape's going to increase. And the question is, what does the first mode shape look like, and what does the other mode shapes look like as well? And that's what we're going to go through too. So as a start, we just want to understand that this week we're going to be looking to free vibration tests. And we will aim at, from the equations of motions we developed last week, we will aim at developing the natural frequencies or time periods, whichever parameter. So omegas or t, the time period, we will be calculating this week, starting from the equations of motions we stopped at last week. Modes of vibration, it is the shape of vibration. We're going to find dimensionless values, which is phi. Those values will indicate for us the shape of the vibration, right? And that's for a multi-degree freedom system. Now, the systems we're going to be looking at, just for us and for you to understand the process, we're going to be dealing with free vibrated systems. So it's kind of pre-displaced, then you leave it to vibrate. And again, if we're going to start having external force applied, you just need to further develop it similar to how we develop a single degree of freedom system, right? So we're going to just learn the starting point of a free vibration system. And if things need to be further modeled, you just need to apply what was applied for a single degree of freedom system. Same thing. In terms of whether it's damped or not damped, we will be working with undamped systems, right? That's what we're going to be analyzing today. And if you want to incorporate that C term or the C part within the equation of motion, then you can do it by all means. It's just your matrix going to be a bit bigger. That's all, right? So basically, these are the kind of assumptions or what we're going to be considering. It's a free vibration systems, and they are undamped systems. Given that, the equation of motion, from being general, like the one you're seeing here, it will be reduced with considering the mass by acceleration plus stiffness by displacement. So we don't have damping in the equation of motion. So basically, we're just here reminding you that this is the equation of motion that will be applied. But because here we have 2 degree of freedom system, it's going to be the properties M or K, whether the mass is coupled or the stiffness is coupled. It's going to be in a matrix format, right? It's going to be in a matrix format. Not only that, it will also be setted with a special initial conditions, like because we said it will be freely vibrating, so it will be set with a starting displacement and velocity, which is typically what we're going to see with the examples. The velocity will be 0 typically because we're going to start with no motion. So the velocity will be kind of 0. And displacement depends on the question whether there is a pre-displacement, which usually the case because we're studying free vibration. So if we're studying free vibration, we have to start it with some sort of displacement to get it to vibrate after that. All right, so these are kind of just basic understanding about what we're going to be looking at. Again, we're going to be staying with undamped systems, and there will be some initial conditions to start our solutions with. Now, let's have a look if we have randomly. So let's say we had the system, right? You had kind of 2 floors with 2 different mass values, and also each floor got its own stiffness values. Then you decided to, let's have a look to this colored shape. So let's say you randomly have deformed the building to the shape I'm showing you with red, right? You have deformed the building to the shape I'm showing you with red, then suddenly you released it. You suddenly released it. So it's going to go from shape A, which I started at. Have a look to the graph as well. So see what's happening at point or time A. This is time A. And we have randomly reshaped it like this. You can see the displacement at level 2 was with a value 2, and displacement at level 1 was with a negative value, maybe 0.5. Then we suddenly removed it. What's going to happen? Each floor going to be moving randomly by its own, right? There is no kind of similarity between this level and that level, between level 2 and level 1. Because at C, at points, for example, B, let's talk about B. At point B, you will have the first floor or the floor number 2 almost 0, while the first floor being maximum negative. And if you keep going a bit more with time, your second floor gonna be a bit negative, then the first floor gonna be a bit positive. I'm talking about this one. So the point is, there is no kind of harmonic motion, something like what we experienced in, just let me show it to you here. That's exactly what I want to show you. You remember with the single degree of freedom system, when we studied single degree of freedom systems several weeks ago, if we had a system like this, and you've as I said, you have pre-displaced it like that, then you released your hand. It will, and as we said, there are no damping, it's a freely vibrating. So it's gonna give you that harmonic motion. You're gonna have that consistency in terms of amplitudes and the time period. And remember, this is what we start talking about in weeks 3 to 4. All right, so that's one of the key differences we're having from a single degree of freedom system. If you displace it with whatever values, it will always give you that harmonic motion. Unlike with what we're seeing for a multi-degree of freedom system, if you have randomly displaced it, I'm saying randomly, so without specific rule. Next, I will talk to you, there are cases or situations where the shape will give you some sort of consistency. But now, if we randomly displace it with the shape A, this shape I started talking about before, if we displaced it with shape A, then your motion gonna be randomly displaced, where you won't have any consistency between the amplitudes. Like when it's positive here, maximum, here you got maybe negative. So here it was 0, here it was negative. Here it is maximum, here it's less than a positive, this is positive, and this is negative. So there's no kind of similarity between the floors, and there's no harmonic response in the motion. Now, so at this stage, we just want you to distinguish what's differently happening with multi-degree of freedom system, right? And another way of explaining this is the ratios between displacement at level 1 and level 2, they are typically changing over time. Right, so this is another way of explaining what we're finding is the deflection shape, which is the ratio between the first floor shape and the second floor shape, that it is changing with time, which is an evidence that the shapes are variable from one point of a time to another, right? So when we can decide, or when do you think, or when the consistency can happen? So that's the key question we're trying to figure out. For example, let's have a look for this shape. The question is it possible for the shape of deformation to vibrate like this, where you can see some sort of discrepancy? So A is here, then it's going to go to E, then it's going to go to B, then D, then C. So do we have a case where the building going to be vibrating with this kind of homogeneous and harmonic motion? The answer is yes, but you just need to pre-deform it with the correct shape. So what I said to you before at the very start is we have pre-deformed the building in a random shape, where here we have set a distance and positive, and here we have a negative distance, which is here, just this part. It was deformed here, and then we released it to vibrate. It gave you the non-harmonic motion response, which is here. What I want you to understand is, yes, there is actually a situation where if you have pre-deformed the shape prior to releasing it for free vibration, if you have pre-deformed it to a shape that will give you harmonic motion, then you will end up having such unified motion. Now the question is, what's that shape? How to figure it out? That's what we're going to learn how to calculate today or this week from the equations of motion. And to cut it short, this is what we call the mode shapes. So in other words, if you deformed a building to their mode shapes, which can be calculated analytically, then your building going to be vibrating with harmonic motions. And to also make it, or maybe let me ask you this question, if people are, why do you think we have to look to such shapes? Any idea why? Because what I'm telling you, each multi-degree of freedom system got a number of mode shapes. By the way, this was the first mode shape, and there's another mode shape here. Now there are two mode shapes, just to let you know, because it is a 2D problem and there are 2 degrees of freedom system. So you've got 2 masses which can be freely moving, like what we talked about last week. We said the number of degrees of freedom, it depends on how many masses we got in the system that can be freely moving. And here we have 2, 1, 2. So we all agree this is a 2 degree of freedom system. How many mode shape it's got? It's got 2 as well. It's got 2 mode shapes because we have 2 clear defined masses in the system, which is second floor and the first floor. So we all agree about this. We all agree it's a 2 degree of freedom system, and we all agree because of we are sure, theoretically assuming that we had 2 degrees of freedom system, then we have 2 mode shapes. Now the mode shapes, they are as shown here. And in the computation process we're going to go through, we will show you how to determine the values of those mode shapes, because they are the critical shapes we have to find. Why? That's my question. Can anyone tell me why we are bothered to actually find where is that mode shape or the value of the mode shape? Can anyone just jump in and tell us why would you be worried about finding the mode shape for the system. And that's basically what we're going to be showing to you soon when we get to calculations. That's basically what we're doing here, and we're trying to find the mode shapes. So in other words, why we're learning this week, why we need to find the mode shapes. Basically, because it will give you the most adverse deformation a building can be experiencing. Yeah, we're trying to find the mode shapes because they will help you to calculate the time period for the building when it's obviously vibrating at such mode, and that will give you the most adverse effect. And as you know, we need to know the time period, we need to know the frequency, because after you know it, you can compare it with the forcing frequency. And if they are matching, that's a problem. You're going to have the resonance problem. And if it's matching, then we have to change something with the building that will keep the time period of the frequency of the building, the natural frequency of the building, away from the forcing frequency, whether from earthquake or wind or whatever it was, and then get things to be more stable and static or with limited vibration. So the mode shape, usually it is the most likely shape of vibration to happen, the weakest, and usually the weakest one, it is the mode shape number 1. Now, in this case, or in other words, you can say the easiest shape for the building to vibrate at. Which one is it? It's actually this one. I know this can be observed by just visually looking to the 2 degree of freedom system. However, in terms, we need to use math to calculate the shape itself. So we need to know if this is 1, how much this is going to be. Is it half of this distance, or 3% or 75%, or that's what the mode shape. One of them going to be 1, and the other will be part of that 1 value. We will do this mathematically, and that's what we're going to be working out. But I just want to understand mode shapes. Any multi-degree of freedom system got a number of mode shapes. Now, if we have definitely defined the floors by lumped mass, if those lumped masses were 3, then you're going to have 3 mode shapes. If the lumped mass are 2, you're going to have 2. If you have 10, you're going to have 10. Now, in your RCB building, you have if you ask the software to give you 30 mode shapes, it will give it to you. Why? Because there is always walls which are moving independently of the building. Because whatever we did, we can't 100%, because that software is actually doing a matrix for each wall, for each column, for each slab. So there's always mode shapes, even for the floor themselves. The floor itself got its own mode shapes. That's why with the software like RCB, even if you ask if it was 10-story building, someone will say this should have only 10. But when you go to the software and ask it for 15 or 20 or 30, it will give it to you. But remember, those other mode shapes, they are to do with the floors or walls. It's nothing to do with the whole building, with the entire building. Only if you go to a software like Space Gas or SAP, if you used it, you don't have this capacity to model a wall and a column. They're going to be modeling something like this, very simplified. In Space Gas, the way it's modeled is just a mass and a stick, a mass and a stick. So definitely here, if the software will give you 0 shapes, if you tell him or tell the software to give you, so this one is 2 degree of freedom system, yeah? But if you build it like this in SAP, in those 2D tools, and you ask the software to give you 5 mode shapes, it will give you 2 and the rest will be 0, 0, 0, because there is no mode shape 3 or 4 or 5. You only have mode shape 1 and 2. But with RCB, it will always give you more. It will keep giving you 2 whatever, because each element you define got its own mode shape, because it's kind of more generic software. However, when we look at it, and I will go through that with you this Wednesday a bit, is you need to find the thing about the worst case scenario or the most severe mode shape. It's the one with the highest time period, as we're going to see as well today. So the most severe mode shape is actually the easiest shape to be profiled. So the easiest shape to be profiled is this one, and this one would have the highest time period and the smallest frequency, because it's kind of the most gentle vibration will happen with this shape, which is really the most severe one to worry about as a designer. And we're trying to check for such mode shape as well as others. Right. So in other words, or in summary, here we've got 2 degree of freedom systems. It's got 2 mode shapes, the one on the left and the one on the right. The first mode shape, it is the easiest to happen. And obviously here, this is the easiest to happen, and that means it will have the highest time period value. So here we're going to have T1 and T2. This one got a time period, and this one got a time period. T1 is the time period for the first mode shape, and T2, it is the time period for the second mode shape. And usually, as I said, the easiest shape to happen is actually defining the first mode shape. Now, again, someone will say experimentally, how if we build like a smaller frame and want to find out when the first shape to happen, that's when you have pre-positioned the structure, like the one I'm showing you with orange. If you manage to pre-position the frame to the levels at which phi 21 and phi 11 gonna be same as how the first mode shape gonna be defined, then you release your hand, it will stay vibrating with the shape. So you will have this kind of homogeneous vibration, which I was talking about for a single degree of freedom system, right? So if you, and you can all imagine this is possible if you have pre-displaced a stick with shape 21 at second level and shape 11 at the first level, and you release your hand, the frame or the building gonna be going back and forth with this shape. This shape will stay as it is. It won't be randomized as what we experienced if we have randomly pre-deformed the shape and released it. So this will give us a harmonic motion. And this, as I said, because it's the most severe, it will be the first mode shape. Same thing, experimentally, if we have a pre-displaced the top floor to phi 21, 22, and the lower floor to, I will make it in blue here. So if we pre-deformed the frame as shown here, so the second floor with phi 22, the first floor with phi 12, and we release the hand, it will give us that harmonic motion. It will keep moving with the shape you see on the screen always. Now someone will ask, what's this value and what's this value? These values will be calculated because it's got specific ratios and shapes to give you the specific harmonic motion. Now there are, or in summary, or again, in other words, is 2 degree of freedom systems got 2 mode shapes. Each mode got its own time period. And what experimentally or physically it means that if you will be deforming your frame to that shape, that particular shape, when I say that particular shape, it means phi 22 and phi 11, you will always have that shape happening after you release the pre-displacement. Same thing apply here. If you pre-deformed your shape to this profile, well, the node means there is zero displacement at this point, right? At this height, again, it depends on the height. Where is it? Which is all can be estimated by math. So second mode shape got its own time period, and it will, yeah, if you pre-displaced it with phi 22 at the top and phi 12 at first floor, then and you release the you release the constraints, then it will be vibrating always with this shape as you see from A to B to C to D to E. Okay, any questions? Now let me ask you quick ones. Let me ask you quick questions. Which one you think it's the first mode? The one on the left or the one on the right? Which shape got which one is the first mode? Which shape you think it's easier to happen for a structure, for this structure, this 2 degree of freedom structure? What is the most severe shape for it to vibrate at? Or in other words, which shape you think it's easier to happen, more likely to happen?
Oh, the leftmost shape.
Sorry?
The left one.
The left one, that's right. So this is the most likely to happen mode shape, and that's why it is the first mode shape. And it's then the second question, which one got the highest time period? Is it the one still on the left or on the right? The highest time
Still
period.
on the left.
That's right. What about the highest frequency?
The right one.
Excellent. Basically, if you all have this under common understanding, I think you will figure it. You should be on top of this this topic. And just to give you a bit of heads up, which I will be talking more about next week, is definitely you will have a question related to multi-degree or 2 degree of freedom systems in the final exam. So we know students do usually get some workload at the end of the semester because of late submissions, whatever, but don't bypass the topic, because you can claim some marks from such knowledge, and you can see it's straightforward. You just need to go on top of that math business behind it. Okay, so we all agree about what this slide is telling us, and here basically it's kind of repeating what I said to you, but with some graphs that can help. Basically, what does it say? It says here that you can say A. So this is the first mode shape that we all understand now. And at time A, where we got this shape, if we have managed to pre-deform it, the starting point will be here, right? And then we will have the same kind of with reduced amplitude happening at B, then a bit reduced more at C. Then you see that we got this kind of harmonic motion happening over the time, unlike again what you would experience if the frame was pre-deformed in non-natural mode shape. right? So it's going to be randomly vibrating. And here you've got the harmonic motion between the first floor and the second floor. Same thing applies for the second mode here. If it was pre-deformed with this arrangement, then you will have this kind of harmonic motion happening bit over the time at different points. And that's where we can say it is a natural mode of vibration, right? Now, the other one, the very first one I was talking about like this, yes, this one, it's very difficult to happen, and we're not worried about it, because even if it's happened, its frequency gonna be very, very high, or the time period won't be significant at all, because it's not a problem that I'm worried about. It's not something that as a designer, I'm worried about. So there won't be resonance happening with such response. Yeah, so basically, after we understand when the second mode gonna happen, when the first mode gonna happen, we all know this relationship. Whether what we're trying to say is for each mode shape, whether mode shape 1, mode shape 2, we do have a specific time period. As you can see, the time period from this peak to this peak, it is T1. Then from this peak to this peak, it is T2. That's why we are claiming there is a harmonic motion between the first floor and the second floor, because you have defined kind of cycles. You have a more defined cycles where you can come up with your applicable time periods, and you can say there is actually a time period. And that's what we're saying here. T1 means it's the time period for the first mode, and basically it can be calculated, converted as well to frequency. You know, you can reverse or change from time period to frequency, depends on what you really want to answer. Same thing, same story was for the second mode shape. There is, again, you can clearly define a starting point and an ending point for each cycle. And because we have this harmonic, the peaks start to be consistent as you go. You can define a natural time period, but in this time it is the second mode. It is the second mode. All right. And I think this one again is showing you a difference between the first mode. See, this is the time for the first mode, which is again longer than the time for the second mode. So the time it takes the first mode to finish is almost a double of what it needs for the second one. And that will be reversed in the frequency. So here you're going to be having a lower frequency than what you have for a second mode shape. All right. And we're going to be, and again, that's the second outcome from our calculation. So it's actually the first one. When we're going to start working on the math, the first thing we're going to aiming at is finding the time period, because it will tell us for the first mode shape, this is the time period. For the second mode shape, you will have another time period, T2. So you're going to see with our computations, the first thing we do is we find the time period. Then after we find the time periods for 1 and 2, we're going to go and find the mode shapes for 1 and 2. Phi 22 and Phi 12, and then Phi 12 and Phi 11. All right, so yeah, this is just a summary about what I was again talking to you about. The longer of the two natural vibrations is denoted by T1, which is the first the natural time period for the first mode, and the shorter will be the time period for the second mode shape. Okay, and it will be a reversed definition for the frequencies, but mostly what we work with, it really depends on the question. Sometimes we ask you for time period. Sometimes we ask you for a frequency. I think mostly what we can calculate for is the frequencies, right? So now we're going to see what we mathematically do. Now, most of what we're going to see from this point, it is all about math. You just need, again, to remember the math exercise. But if you follow the example, yeah, you're going to see it's really straightforward, and you should be able to work it out. If you have any difficulties with math, you can just ask me. If you get on top of it, you should be fine. It won't change. Again, we won't ask you. In terms of the math process, it is going to be same. Not similar, same. I don't want you to go learn different math methods. But the dynamic questions will be similar. So especially with those questions, yes, we're most likely going to make sure you know how to do what we did here together, but there may be some practical questions we like to ask you about. Like what I just asked you a few minutes ago. I said to you, which one is more severe, which one is got the highest frequency, which one is easy to happen, which one is likely to happen. So these kind of questions, like a practical questions that we like to ask you. Okay, so from this slide, we will be talking about determining the frequency and the mode shape. So we're just going to go back to the equations. And the equation that can define for us the shape n. So phi n, it is n is the number of shapes. If you've got 2, it's going to be 2. If you've got 3, it's going to be 3, and so on. Right? And q is the time. So as we know, the fraction of the mode shape going to be changing over time. So this quantity will be the time variation of the displacement. And this is basically the final displacement that was caused by particular mode shape. Now, from last week section and also in the textbook, which it's all basically written here for you, how we relate these two properties. So the key properties we have here is the frequency, and we have the mode shape, which is phi. Phi is the mode shape, and omega is the frequency. So how they are kind of both related to each other. And I think here we've defined for you equation 2 based on such definition. You don't need to prove that, but it's kind of mathematically proven in the textbook. So equation 2 can be solved or re-represented, because what we really want to find, there is somehow a relationship between displacement and stiffness, right? There is a way where we can relate displacement with the stiffness by incorporating the mass. So there is a mathematical process where we can convert equation 2 to equation 3, and that's what happened here, which is the key equation we're using today to find our shape and omega. Again, what we really want to find this week, it is the frequencies and the shape, which is here or there. Now, our starting equation is this one, which is defining the displacement over time in function of the shape. And by incorporating the stiffness and the mass, we are able to rearrange this equation to equation number 3. From here, which is, again, this is equation number 3. This is mathematically called as a matrix eigenvalue problem. And the way it's solved, it's by separating the both properties from each other. So you can separate this side, and you have another side, and we can use a trivial solution for this. A trivial solution will tell you it's either for this to be 0 or for this to be 0. Now, we all agree that the phi cannot be 0, because something gonna get vibrated and something gonna move. So the shape cannot be 0. There is no way for this shape to be 0. There is always a value for phi. So we can take away this solution. For the phi to be 0, it's not possible. So we can take it away from the calculation. And later on, we're going to find out what was actually this value. What's possible for it to be 0? Now, why we want to make it 0? again, so we need to understand this. Why we equating this component to 0? That's where we're going to have the mode shape happening. That's when we're going to have that harmonic motion to exist. This is kind of the physical application for math. It is, in order to achieve a mode shape, we have to equate this material or this component to 0. Now from here, it's either for the shape to be 0, which is not possible, or for this term to be 0, which is possible, and that's what we're going to work out for. So as a determinate solution, equation 5, it is the way to go, where this term, this determinate solution can be equal to 0. What's next? From here, we are able, after we equate this to 0, you're going to see we're going to use some sort of quadratic solution methods to find for K or find for M. And that's what basically you're going to be seeing. I think if you don't need to go and master the math behind this, I just want you to know the process of how we applying this solution into solving. You're just going to be doing this, the more simplified math, and that's what you're going to need to prepare yourself for. If we're talking about the final exam, you just need to find the roots, right? For this equation number 5, we just need to find the real positive roots for omega, because that's what we're after, aren't we? We are after this. Remember, our aim is to find frequency. This is going to be a property of what we find last week. This is the mass property of what we found last week as well. What we need to find for the case where we had harmonic motion. So the harmonic motion was achieved by equating this equation to 0. Now we all agree that the phi cannot be 0 because there is a vibration and there is a shape. Then what's the other option we have is to solve the equation further, is to put this term equal to 0. Now, then this equation is ready for us to determine the frequency, whether mode shape 1 or mode shape 2. And from frequency, we can find time 1 and time 2. So the process from there is just basically all about rearranging, substituting, and once we substituted for the matrices we had from last week, so if we're going to substitute for the matrix K and matrix M, we will be in a situation where we have very different equations that will require you to use algebra plus quadratic equations. That's basically what you're going to be doing. And then you're going to see you just need to find the answers that we need to find. So I think the best way to get on top of the math business, it is to go through this. I can say 85% of what we're doing here is based on remembering math, and you have now all the time to do this. So I think here I provided you with all the solutions you may need to look at. And if you know how to do it, maybe like last week, you will have another 2 versions of questions in your workshop. If you are on top of those solutions and you know how you do them, you should be ready for the final exam. And also you should understand how RCB was working. So RCB basically is doing what this is doing, right? RCB basically, because it's the only difference is with RCB, as I said, it's got 10 floors and it's building a much bigger matrix, which got 10 by 10 couples. You're coupling 10 equations together. Now, as I said to you, RCB, if you ask him to find 40 degrees of freedom system, the properties for 40 floors, or sorry, for 40 degrees, I know you modeled it as 10 story, but even if you ask him to find 40 degree of freedom or 40 mode shapes, it will give you these numbers. But remember, they are not for the entire building. you will start looking at, because the software gonna repeat all those calculations, and it will go like look at element by element. It will start looking at the ground floor and check wall by wall and column by column, and we'll consider that this is an element by itself. But usually the building will be more flexible than a piece of column which is only 3 meters high, because your building was much higher. So it's more severe. Again, it's easier shape to happen. Usually the software will set the first mode as it's easier to happen, and then take it from there. So really simple. Have a look to what happened here and prepare any questions you want to prepare for me, but I will still go through these slides just to show you the links between what we're doing this week and the previous week, and we progress from here. You can see the final aim typically is to find the mode shapes, right? So if the shape here was 1, they are typically going to be scaled to the value 1. So if it's 1 here, this is 50%. That's the first mode for that frame. If it's 1 here, it's going to be -1. So it's usually scaled to 1% or 100%. So this is -1. This is the second mode. That's what we really want you to know from weeks 10 and 11. We want you to aim at finding the frequencies for the second mode and the first mode. In the final exam, maybe you will be having numbers. So instead of letting you start with some constant values like K or M, we will give you particular values. Like we tell, like a real building. We tell you this is maybe 2,000 kilograms, and here it's going to be maybe 1,000 kilograms, and so on. Right. So have a look. Let's have a break. Maybe we'll meet back at about 3. How many minutes you want? Yeah. Let's meet 3:10. And yeah, I will just go through the solutions. Yeah, make sure you prepare any questions you do have there. All right, so the first example we have here, 11.1, it is, as I said, continuation for the example we looked at last week, which is week 10. Example number 1, simply we started from a frame like this. The second floor mass is half of the first floor. Same applies for the stiffness of the posts. And we've gone through a process where we determine the equation of motion for the 2 degree of freedom system, where the mass matrix is shown here and the stiffness matrix is shown here. In summary, how we calculated this, you have 2 options. One is you use the influence coefficients. The second is you use equations given to you last week. Make sure you know both, because in the final exam you may be asked to use one of them. All right, so in the final exam, you're going to ask me, will we be given those or we have to do it from the start? Depends. You may need to start from what you did last week and continue to do what we're doing this week, or you may be given, so please read the question in the final exam. You may be given the mass and stiffness matrix, and you don't need to do what you did last week. So just setting up our matrices from week 10. We all know last week the stiffness was defined by this elastic formula, which will be given to you regardless. Then here, simply, in order to start our solution, we just want to apply the matrices we have, or the coupled equations of motions we have on this determinant equation. That's what we're doing here. We just want to apply equation number 5. So before we use equation number 5, we just want to set this matrix, right? We just want to set this determinant solution in the matrix, and that's what we are doing here. So this matrix arrangement can be defined by what we're seeing here. How we do this? To find the first part of the couple, it is 3k, which is this value. So you basically just need to algebraically consider these two properties together. So it's a 3k minus 2m omega square. So that's what we have here. If we go to this part of the matrix, as you can see here, it's going to be negative k and nothing coming from the mass. So this is 0. That's why all this is going to go for the for this part of the matrix. This one, same. We got negative k and we got nothing from the mass. So you're going to end up having this side is 0 and you're going to end up having negative k. This part of the matrix is coming from, you've got 1 unit of k and 1 unit of mass. So if you substitute it into this equation, it's just going to be k negative omega square, and it's just same. Right? So this is our kind of matrix. Now what we're doing here is we're just resolving the matrix. We know all this matrix is going to be equal to 0. And what we did here is just we opened the matrix into one single equation. Right? So we just going through the algebraic process of resolving the matrix to convert it into an equation, and you will end up determining this equation here. All right. Which is all about multiplying this by that and minus this by this. Basically, that's what's going on. So this multiplied by that is just all about opening a matrix or resolving a matrix into an algebraic format like here. And all that will be equated by 0. Then yeah, just try to be careful with those steps because it's again pure math process. You're just going to be refining and rearranging to end up. Typically, with all the questions we're going to be solving, we're going to end up with this quadratic equation, and you will be solving by this. Now, in case people don't have, you don't need to memorize this. Maybe these are the things you can put on your paper, on your notes paper, which you are allowed to bring to the final exam, and I will talk about this again next week. So, but make sure you understand this simple algebraic process. But where we're going to end up, we get that's basically what we're going to end up with. And we all know that we typically have 2 solutions for the natural frequency because we have 2 mode shapes anyway. All right, so we then gonna come to this. We just need to solve from the quadratic equation, and our one of the solutions is we finding the omega squared to be 2k, and the second solution will be the 2k over m, and the other one was k over 2m. Now from above, we can find the first frequency, which is ending up to be this figure. Or now here we're just showing it in terms of the k, or we're replacing, because we know what the k is from the start. We know what the k is. We can replace it by k. whichever you're going to be showing, it should be fine unless the question specifically told you what to show. As I said, most likely you're going to, not most likely, maybe, there's nothing most likely. Maybe you're going to be given these values straight away. So you just end up to find a value. So by here, we have calculated the frequencies, whether frequency 1 and frequency 2. As you can see here, which one? Yeah, you can see the first mode shape got the highest frequency, got the smallest frequency, sorry, which means the highest time period. As we said, the time period is the reverse of frequency. So frequency 1 is less than frequency 2, which is the frequency for the second mode shape. And which means that if you're going to just reverse those values, it's going to give you a higher time period for the first mode shape. And so far here we have estimated the frequencies or the time periods, whichever we needed. Then the next section here is all about finding the mode shape, which is a continuation for, also we just need to adopt some math process, and we're starting here with equation number 4, where this determinant solution going to be again equal to 0, but here we have our mode shape defined, and you all need to know by now, we know what's the frequency, and we know all those matrices value. So we know what's the stiffness value, and we know as well what is the frequencies for the first or second mode shape. Now, first step is we taking the frequency to be equal to the first mode's frequency. All right, so we are trying to find the first mode shape. When we are finding the first mode shape, the second number typically gonna be 1. The second number of the phi gonna typically be 1, and this is reflecting the level. So this is the level 1, and this is level 2, level 1, level 2, and the second number reflecting the mode shape. All right, so we're gonna just substitute into this equation, and you just follow this arrangement we have here. You will end up building these matrices. Okay. And the omega is also calculated. So we typically will know omega, and by simplifying the equation here. So because here we substitute for omega, because in this case here we had the omega to be like omega 1, for example, it was root k over 2m, and because it's squared, it's going to be k to m, and it can go away here, so things can be simplified to be 2k, because the 3k take away k. For example, I'm just letting you just remember or refresh. I know most of you, maybe all of you, haven't. Typically, students get on top of this after they give it some careful thoughts. But the mathematical steps we're doing here gonna stay same in the exam. It's only about the application of what you're going to be getting at the end of the solution. So basically, we're applying this equation on determining the entire matrix for the first mode shape at 2 different levels, level 1 and level 2. Now, we ended up with this equation, this double coupled matrix equation. And to find, again, remember our aim is we need to find the value of the mode shapes. The way to find it is we have to assume one of the phi's to be a scale of 1 or 100%, whichever some textbooks uses, like they're gonna like. So what we're doing here, basically, we know this is for the second floor, and we're assuming for the second floor mode shape 1, the phi gonna be 100% or 1. Some textbooks calls 100 like 100% value. Some others use 1, and the rest gonna be fraction. So what we expect, we can expect the other will be another number, but we need to scale it based on this figure. So for phi 11, to find, we're trying to say here, to find mode shape at level 1, mode shape 1, we're going to assume mode shape 1, level 2 to be 1, right? So level 2, mode shape 1, going to be 1. And we apply this in any equation within the matrix couple 1. So whether you apply it on this equation or you apply it on this equation, whichever. And that's what we did here. So 2k phi 11 minus k, because here we've got phi, we multiply this by that, and then we multiply this by that. So this is going to give you one equation. If you want to find, we have two equations here. You multiply this by this, the 1, phi 1, and you multiply this unit of the equation by phi 21, and all that going to be equation. So basically, we convert the coupled matrix to one equation. Either you can use the second one, this by that and this by that. It's up to you. Typically going to give you the same answer. What we did now, we just took one equation of the coupled matrix, and that was the equation I'm talking about here. Then from this equation, you will have one unknown, which is the phi 0, 0, and it came to be half. Right, so this is again the shape at level 1, mode shape 1. The shape at level 1, mode shape 1, it is half. So when the mode shape level 2, mode shape 1 was 1, the lower one was actually half, which is making sense. Right, so the mode shapes, this one will give you the final definition for the mode shape of the structure. At level 1, phi 1, you will have half, and at level 2, sorry, you will have phi 2, 1, right? Which is basically showing you the shape. So by now we have find all those values, which is making sense. It is the first mode shape, which is the easier to have it. All right, same technique, same process is applied now to find omega, to find the shapes of the second mode, and that's what we're doing here. So I don't, if you have managed to do this, understand all this, I suggest you not to look at the rest and go to the rest, and you will end up finding these shapes. Okay. So that was the first example, and the second example, it is a continuation for our second example from week 10 as well. So this was just the second one from week 10, and the process will be same. I should say same, not similar. So exactly same in terms of the math skill. Now, what I want you to do is just to look at those numbers, and just let me know if you don't feel comfortable with the math. If you see anything strange here, the key thing really as a dynamic skill is you need to know how those equations are formulated, because you need to understand the softwares. I know someone going to be designing 10-story, 5-story, 6-story building. You will ask the question, do we do this? Do we do this by hand? Usually we do things by hand up to 2-story, up to multi-story developments. And as I said, this is not only done for buildings, it can be done also for having a generator sitting on a floor, because when you're going to put the generator on a flexible support, you will end up like this question. This can mean a lot of applications, and usually it is a 2 degree of freedom system, because this is one system. Sorry, actually, I was trying to do. This is 1 degree, and this is our 2nd degree. And there's a lot of hard calculations that can be used here, where you solve real problems. Yes, if we go to more than 3-4-story buildings, then we will use a software to do all those matrices. I know we won't be but you need to know how it's really working. Unless you want to be a software designer, it's like, you know, the person who inductor person, he's basically a structural engineer who have been working on developing these inductor softwares. So I just want to know if any students got any questions within what I've really took you through here. Just jump in and let me know. If not, I purely suggest you not to look at the solution here. Yeah, you do it based on what just so you get on top of the calculations, and again, that's all enough. Just make sure you understand the application of each properties, and what does it physically mean. Understand the difference between the first mode, the second mode, in terms of its properties, its significance, its engineering application. As we said, usually the first mode will be more severe to happen, and there's a lot of cases where we found the mode shape is more critical. The first mode is more critical, so we try to stiffen up. Stiffen up means we change the stiffness. We change all those values here. By the time you change the stiffener, you're going to be changing everything we have here. If you double it, if you replace a steel with concrete, if you use composite steel instead of hollow section steel, that's where those decisions can come, right? So because it's going to change if you found in your multi-degree freedom system, or it is resonating with the exciting force, then you just kind of play with the stiffness usually to get it to work. So, any questions?